So I'm going to tell you a few design issues and peculiarities of the siesta interface to AIDA. Siesta is the AFT code that uses pseudo-atomic orbitals as Basissets. That's the main difference with respect to plane wave codes. So let me get into it, give you an overview. Can you read this small print? Well, as a DFT code, we work with outputs like total energies, wave functions, forces, stresses, spin polarization. All that is covered in the plugin. We can also do geometry relaxations, including variable cell, although we still cannot do, as I said this morning, we cannot do molecular dynamics. Siesta can do them, but the plugin is not set to, well, it will allow you to run a molecular dynamics thing, but it won't report correctly the results. The parser will not understand what's a molecular dynamics run. I won't show you the code because Leopold already has shown you a very small example which already is not completely trivial. So if you look at the code for Siesta, you will probably not understand much. The basic idea is that the plugin is preparing the input file for Siesta, right? And at the end is checking some output magnitudes out of the many files that Siesta produces, is selecting a few items to report back to the repository and the database. Let me go ahead a little bit and show you the entry points. We have, Siesta is a pseudopotential code. So one of the things we did was to create this special data object that holds a pseudopotential file in a specific format that Siesta uses. It's called the PSF for historical reasons. This is similar to the UPF data object that is created with the Quantum Espresso plugin. In fact, we just copied the whole code, basically. We provide families of pseudopotentials and the basic stuff. Then we also have to accompany this, we have an extension to the data, the Verdi data command to handle these things, the families, and check whether the pseudopotential is in there, etc. Then the more important stuff are the actual plugins. Siesta is a big program, and it has basic functionality which is covered by this Siesta plugin. It's called the class name is Siesta Calculation, but we also have a plugin for an auxiliary program that is able to post-process part of Siesta output. In particular, Siesta can create what's called the local density of states, which is some kind of charge density but restricted to wave functions in a particular window. That's, for example, used to simulate STM images. So this plugin will take that file from Siesta Calculation and create a user-friendly view of the STM simulation. And this other object is something that computes phonon frequencies from the output of the force constant matrix that Siesta can produce in a special way. So these are three different plugins within the package. And corresponding to these plugins for calculations, we have parsers. So this is the one-to-one correspondence to the parsers. For the main Siesta plugin, this is the signature that is produced by the Verdi plugin list aida.calculations siesta.siesta command. This is what Leopold also showed for the diff plugin. This is more involved, and you see that it has, well, presumably when you look at this, you get a relatively good overview of what the plugin does. Obviously, you need a code. Obviously, you need some running parameters, like, for example, cutoffs and other quality parameters. You need pseudopotentials. You need a structure, obviously. And then there is a bunch of optional things. K-points. Well, if you don't specify K-points, Siesta will use just the gamma point for the calculation. That's a design decision. Well, we could have required a K-point object always and just check whether it was one K-point or not. But if it's not there, we just do the easy thing. Also optional is the basis set specification. In Siesta, basis sets are very important. You should really work on them because the better the basis set, the more accurate the calculation it is. But by default, we have some heuristics that can give you a relatively decent basis set for you. So if you don't specify anything, Siesta will automatically create a basis set for you. Hence, this thing is optional. For the k-points, this is the k-points for the normal calculation. If you are requiring a band structure calculation, then you need bands k-points. It's also optional, and the existence of this node determines whether Siesta is going to do a band structure calculation or not. Metadata is also optional, and this is special settings for optional stuff too. And this is something that is required in most plugins that are able to be restarted. This is important because you might find that a particular calculation is not converged, so you need to restart, possibly copying from the folder in which you run the calculation the latest density matrix file that you got in the process. The density matrix contains the sort of snapshot of the electronic structure as you do the self-consistent field loop. So if you reuse that, you are further ahead in the self-consistency, and presumably in the next run of the calculation you will converge. And the same with intermediate structures and so on. So this is a bit esoteric at first sight, but it's very important for restarts. And the outputs are a dictionary with selected outputs like total energy, Fermi energy, spin polarization, things like that. A forces and stress object which contains a couple of arrays in NumPy format which are wrapped in this array data object. This is standard AIDA core thing, which the forces and stresses. It's optional because not all calculations produce forces and stresses. You get a bands array with the bands data object, which is also standard in AIDA, and you will find that there are already utilities to plot band structure, so you don't need to do your own from scratch. So by producing this, we basically produce this object by parsing our own file format for band output into AIDA's format. And then we benefit from AIDA's post-processing capabilities. It's also optional because we don't always do a band structure calculation. And if you are doing a geometry relaxation, for example, you are relaxing a bunch of things, a bunch of atoms, and find the ground state for the no force, the optimal geometry, you get this structure data object with the final geometry of your calculation. Also quite important in connection with this restarting capability are the error codes that you get. This is very simplified. In fact, I have just realized during this week that I need to do a lot of work to do a full taxonomy of the failure modes of the code. That's very important if you hope to cover most cases and allow the user to act on malfunctions of the program. Obviously, not all programs are perfect. Siesta is not. And it might not converge because the system is hard to converge or because you forgot to specify a high enough number of iterations. Many things can go wrong, and these are the last two. These three first codes, I suspect, are AIDA core's standard things, right? I think they are because they have low numbers. I'm not exactly sure because my collaborators did some work on this plugin recently, whether this is AIDA or not, but it looks low level. Let's look at these two, the last two. 120, these are arbitrary numbers. Calculation did not reach self-consistent field convergence. Maybe you are trying to converge a magnetic system, you specified 100 iterations, and it didn't quite converge. So, by catching this, a workflow can act on it and either restart the calculation, maybe change the algorithm for convergence, depending on how smart the workflow is. And I think that that's an elephant in the room because we have not talked during this week about the actual brain power involved in designing a workflow. We are concentrating on the technical part, but for example, to design a black box that always converges is not trivial at all. You know that, right? What do? You make the mixing parameter smaller, you kick it out of the bottlenecking which it is, you switch gears to a different method altogether, you start mixing the Hamiltonian instead of the density matrix or the charge density, you apply a new preconditioner. There are many possibilities, and in principle, if you were super smart, you would put them all there and it will converge. But obviously, we are not there yet. So this is the main structure of the plugin. And now, a few particularities of Siesta. This is a one I like a lot. I mean, this is a code which can use basis sets made of atomic orbitals. Now, imagine that you are simulating a slab for a surface simulation. You might want to give the atoms on the surface a different basis set than the atoms in the bulk, right? Maybe a more complete basis. So then you imagine this is a piece of graphite with some hydrogens. One of the atoms you single out and you call it C red, just to single it out. And you can specify for this particular atom a different quality of basis set. This is the basis set dictionary for input. The basis has more parameters than the plane wave code. How many parameters do you need for a plane wave code? Just one, the cutoff, right? In Siesta, you need more. And this is just a small fraction of all the possibilities that you can insert in Siesta. But the basic thing here is that these keywords are standard quantum chemistry for single zeta polarized, single zeta. This is the minimum basis that you can use in Siesta. And this is the next highest. So, and this also exhibits how we deal with the input. Sorry?
Yeah, no, I just wanted to point this out as an example of where it doesn't make sense sometimes to just parse a string. Right? You could also decide to parse the things that you put there, right? In the block PAO
yes.
size. But you decided, okay, there it's fine, I'm going to parse a string.
That's right, yeah. I was going to mention that later.
Then
So this goes, as a technical point in the plugin, this thing goes almost verbatim into a dictionary in, well, this is a dictionary in Python. This gets projected into a flat file, the FDF format file in Siesta, including the blocks. And this block has some internal structure, but we are not able to query afterwards what was the basis set for C-red. It's in there somehow, but AIDA doesn't know exactly what it is, because this is just dumped in a block. We are thinking of defining some more granularity for basis set specification in Python so that you can later ask AIDA, which calculation did I run with such and such functional and triple zeta polarized basis sets? And then you will get it. Right now you can't because AIDA doesn't know about this. Anyway, so also there are some peculiarities about using these extra species names for the pseudopotential. Obviously the pseudopotential should be common for both the bulk carbons and the surface carbons. So we need to tell AIDA somehow that the same pseudopotential file is valid for C and C-red. And when we deal with families, this is automatic because usually the first character is the symbol, which is all you need. This is an example of the output, just a very restricted output with the free energy, the Fermi energy, and some timing information. This is something that you can, at your own discretion, add to the outputs of the program. This is very useful because then you can run benchmarks and have automatically extract information from AIDA. This is not exactly for plugins, but with a view to the future, if we want truly automated calculations, we will need to do something similar to what Quantum Espresso does regarding prepackaged quality protocols. This means, for example, that you do not specify in the workflow every little detail about which pseudopotential to use, etc., etc. You specify something like, okay, calculation level good, or excellent, or cheap, or expensive, and then internally the workflow will select some set of pseudopotentials. Our problem in Siesta now is that we have a good database of pseudopotentials, but it's relatively recent, and it depends on a version of Siesta which is still in development. And that's, probably you have heard of this, the Pseudodojo database of pseudopotentials. It's using a relatively new method. Well, it's not new, but it has recently finally been implemented by Don Hammond. It's a multi-projector, norm-conserving pseudopotential kind. And at the same time, we have developed a format based in XML for norm-conserving pseudopotentials, and that's our preferred format to deal with this new database. This new version of Siesta in development will be able to read these files, and then we will have available the full periodic table of pseudopotentials. And then you can play this protocol game of forgetting about, allowing the user not to worry about the pseudopotentials. Just wrapping up, we have another set of issues which are still pending. Obviously, this is work in progress. For Basissets, as I mentioned, we have some interesting ideas to pursue in the technical side, but in the physics side, we have a problem that we cannot really treat Basissets as a black box. We could, but it's not in the Siesta spirit. For example, if you know FHA Ames, they offer a prepackaged set of Basissets for the elements, and they call them tier 1, tier 2, with different sizes and expensive levels, cost levels. The problem is that Basissets depend, the optimal Basisset for an element depends on the environment, the chemical environment it is in. So we are reluctant to treat that as something that you can just download from someplace. Ideally, we provide in Siesta mechanisms to optimize the Basisset for a certain material on the basis of its chemistry. So it will be optimal, and the size of the Basisset will not be too big. If you want to prepackage a Basisset, you typically, that will work everywhere, you probably need to make it much bigger than you should. Obviously, the cost of the calculation is going to depend on the size of the Basisset. So we need more heuristics and try to solve that issue. Then we also need to implement a few more features. The migration to 1.0 in AIDA is almost completed. But as I said before, I'm now discovering that we need to do some more work to streamline the workflows that are built on top of the plugin. This is documented in this place. The documentation is not up to date yet, but it will be in the next week or so. And I think, this is interesting. So you start with your code and say, I need to write a plugin for AIDA. But then while you are doing it, you discover that your code could do things in different ways and be a better code. In particular, you could do proper error reporting. You could package things better for easier parsing, like the information about timing. And you can remodularize your code, maybe use different objects that make more sense. But you discover those things when you move out of your local minima of potential energy and see something else outside, right? And another set of insight is that Siesta, at least, and I suspect that most codes are already implementing workflows in them. So for example, in a simple FDF file as input for Siesta, you can specify, please relax this structure and then do a band structure calculation on it. So that's already the two workflows that most people implement in AIDA, already built in the code, right? So where do we separate? Where would the boundary between the plugin and workflows, and what do we expose as Siesta functionality? That's an ongoing battle that we are, not battle, it's interesting, right? But we need to worry about those things. So thank you very much.